Hello, everybody, and welcome back to the Math and Physics podcast. This is the sixth episode. I'm your host, Parker.
And I'm Ray, and we welcome you back to, as he said, episode 6. So,
Yes.
what are we going to be talking about today?
So today we're going to be talking about all different types of infinity and like how it comes into play in math and physics.
Interesting. So, infinity, right? It's a great concept, but is it more than that? And that's what we aim to answer today.
Yeah, so a lot of people think, or they don't think it, but they kind of assume that infinity is just like a number, right? Like when you say infinity, they just think like one with like 1,000 zeros behind it. But the problem is that you really can't think of infinity as a number because then you run into a lot of problems when you start doing like calculus and stuff like that. So really, just when you hear infinity, don't think of a number because it's really not. It's a concept that just it means just anything that's bigger than anything you could ever imagine, and then times anything that's bigger than anything. Like it's not something you can grasp.
Yeah, but the interesting thing about infinities is that there are, many different types of infinities. Like in the Notebook, right? When that actress that I forgot who like her name, she says that some infinities are bigger than other infinities. Or the guy says it. Well, one of them says it, and pretty much that's actually mathematically correct. Some infinities are indeed larger than other infinities. For example, if we were to look at the graph of x squared versus the graph of x cubed or
Yep.
x to the fourth, the the infinity that x to the fourth reaches on the y-axis will be a lot larger than the infinity that the x to the third or x squared reaches on the y-axis.
Well, not necessarily larger. It just approaches it quicker.
Yeah, it's just a larger concept, and yeah, I guess approaches it quicker as well, but it's just a different type of infinity. That's why adding infinities, subtracting infinities, which we're going to be talking about in the podcast, but that's why those things don't really make sense, because there are various different versions of infinities that we have to, take into consideration.
Yeah, an easy way to think about how some infinities are larger than others is to think about just the natural numbers at first. And you think, okay, if you count an infinite amount of time, like after an infinite amount of time, you will reach quote unquote infinity. And then so that's one infinity. And then you could think about, okay, well, if I count half steps, if I go one, one and a half, two, two and a half, technically you will be counting twice as many numbers. But you will be reaching an infinity that is larger, but it still contains the same amount, well, not the same amount of items, I guess. um
But approaching the same concept, kind of.
yeah, approaching the same concept. And then you could just go like even deeper. Like if you just count every rational number, then there's going to be way more. And then even further than that, if you just count the rational numbers in between 0 and 1, there's an infinite amount. And then there's not really a way to compare which one is bigger. Like if you count from 1, 2, 3 all the way to infinity, is that bigger than counting from 0 to 1, counting every rational number? There's really no way to know.
That's true. That's actually an example I was thinking about too. That there are infinite numbers between 0 and 1 or 1 and 2, but the infinity that 1, 2, 3, 4 also approaches is just a different concept of infinity.
Yeah, and you can even take that like infinitely further, right? Like you
Exactly.
you can be like, okay, there's an infinite amount of numbers in between 1 and 1.0000001. It just doesn't end. And that's kind of like a property of infinity, is that, well, it just doesn't end.
Oh, yeah. And actually, I don't know why I thought of this, but the one example that we did in class where it's 0.999 recurring equals
Yeah.
1. And that, in fact, is true, because you can't find any number between 0.999 recurring and 1. And because you can't find a single number between them, they must be the same number, because that's how we define numbers, as greater or less, right?
Yeah,
So
that's
like,
kind
so
of how.
yeah,
I'll go ahead.
yeah. So I was just trying to give an example. Like, if we take 2 and 5, we can find numbers in between, like 3. Therefore, we know that the numbers have to be different. But in this case, because we can't find anything in the middle, they must be the same. And that entire concept, that 0.999 infinity equals an integer number, is pretty, kind of bizarre.
Yeah, and it's kind of intuitive because you think about how like 0.999 recurring has to equal 1. I mean, I meant to say unintuitive because obviously they look like different numbers, but really they're the same. And you can actually prove this by doing like the infinite series, which
Mm.
is a little bit more advanced. But if you take it as like uh, what is it, like 9/10 plus
Yeah,
9/100 plus 9 over
yeah,
dot dot dot, and then you plug it into like the formula that you proved, which is like whatever whatever, you see that
yeah.
it is equal to 1.
The converging series formula, yeah, and then you get that it equals 1.
Yeah, and so one thing that's really important, where we can use infinity, is in limits. So if you want to see, where a function goes when it tends to infinity, right? You take the limit as it goes to infinity, and then you could find, either if you take like f of x equals x, the limit to infinity is just infinity. But if you take 1/x, the limit is 0. And so you can study functions using infinity and studying where they go, based on uh, the properties of the function itself.
Yeah, that's true. Because a lot of times, what it kind of tells us, especially when, like, for example, if we take, as you said, limit as x approaches infinity, then what we're really looking at is how the function behaves when we have a really large number of x. And this is useful in many, many, many ways, not only in math. And I think this is where we're going to merge it with physics here. I don't know why, but the first thing I thought of was electric fields and far fields, you know? So when
Yeah,
we're taking x or something to infinity, we're trying to find out, when we are very, very, very far away, what does this system look like, right? And in most cases, especially when we're talking about electric fields, it looks like a point charge, which is pretty interesting to think about, and pretty intuitive as well. When you're extremely far away, you can't really tell the difference between a few things. And that entire concept of being infinitely far away and observing the system and seeing how the system changes depending on where your x value is, I think, again, pretty interesting that we can see infinity used in real life scenarios.
yeah. And when we did that in class, we were studying like spherical charges or
Mm,
charge distributions, uh, ring charge distributions, disk charge distributions, and it makes a lot of sense. Like if you have a ring charge in front of you, like obviously it's not going to behave like a single point, but then you zoom out infinitely, you can't tell the difference between a point charge with the same charge as a ring charge if you
yeah,
set them next to each other. If you zoom out to infinity, they will each of them will look exactly the same.
yeah. And that kind of applies to, I guess, I was just thinking about it right now. I don't know if it's really true, but I guess it would apply to gravity as well. Would it?
Yeah, do you remember that problem?
Yeah, I know. That's actually why I'm thinking about it, because of that one problem that we did.
I don't know if we had the same problem on the exam, but basically, I answered a question where it was like if you have a ring mass that was like the mass of our planet.
Wait. Shouldn't we not be discussing the exam
I mean, it's
on
over. We
online?
already
No,
got.
no, no. But like, there was like a huge thing. Remember, on the first page of the exam, we were not allowed to discuss it.
During the exam,
I thought it's even after it's over. Like, it's like a no copyright kind of thing.
there's no way that can be true.
I have no idea.
Okay,
Uh,
well, let's say this, okay? I was thinking the other night,
okay.
what if you had a mass that was in the shape of a ring, okay? And its gravitational field would be, kind of analogous to the electric field of a ring charge.
Oh, I had the same question. Oh, I mean, in my dream, the same dream that we both shared.
Anyways, yeah. So if you were to zoom out to an infinite distance, it would just be the same as like a point charge with this, or a point mass with the same mass as the ring that you have.
Yeah,
But something
yeah.
interesting about that I was thinking about, actually, this is before the exam. Um, when I was doing review, if you have an infinite plane with a uniform charge density, the strength of the electric field does not depend on how far away you are from the plane, which means that if you were 1 centimeter away, it would have a certain strength, which is, I think, the charge density divided by 2 epsilon naught. I think that's. Do you
Yeah,
remember?
yeah,
Yeah.
it
So
is.
it would have a certain strength, and then you could be at any point in space. You can be, 1 million kilometers away, and it
Mm-hmm.
would still have the same strength.
Same. Yeah.
And that kind of, you can kind of imagine it as if you had an infinite wall. If you're standing in front of a wall that was lit up at a certain intensity, if you keep on zooming out, because the wall is infinite, right? No matter how far away you are from the wall, you can look down and you could just, see the wall extending infinitely in every direction. So you can't tell how far away you are from the wall because it is infinite, right?
Yeah, and pretty much also, however far away you are from the wall, the intensity remains constant. And I think that's the really cool concept, you know, that the
Yeah.
intensity doesn't change however far you are, which is the same with the electric field.
Yeah. And yeah, so going back to limits, I want to say something about
Okay,
limits
okay.
before we get too far. Um, when you study a function, let's say like 1 over x, just to make it easy, if you study its behavior as it goes to infinity, the answer would just be 0, right? The limit as x goes to infinity is 0. But an interesting fact to consider is that 1 over x is never actually equal to 0. It's
Yeah.
just the limit. And that's an important differentiation that you have to make between, what it actually equals to and what it tends to.
Yeah, because basically what it sorry, continue, continue.
No, go ahead, go ahead.
Yes, yeah, yeah. So basically, what it's saying is that when because infinity, and that's pretty much what we're trying to convince the audience, whoever's listening to this, that infinity not really a number, simply a concept. The same way it can't really reach infinity, it can't really reach zero. That's why it never really touches zero, because infinity, as we said, we repeatedly keep saying, is simply just a concept. So when it reaches this so-called concept, it would so-called be extremely close or equal to zero. But because this infinity is simply a concept, it never truly touches zero for any real number. For any real number that we can think of, it's never equal to zero. And that's why the infinite concept is important.
The reason why we say it's equal to 0 is because when you look at infinity, it is so incredibly close to 0
Hmm.
that you might as well say it's 0, right? It's going to be 0 point, an infinite amount of zeros, and then a 1, but not even, right?
Wait, 1 minute, 1 minute. I just thought of something.
Yeah.
In the same way, wait, 1 minute. No, I'm probably wrong. No, I'm probably wrong.
What are you
Okay,
thinking?
okay, because this is what I was thinking. I'm just gonna think out loud. I may be wrong, just discretion, but I'm just gonna say it. In the same way that 9.999 recurring, sorry, 0.999 recurring equals one, wouldn't 0. Oh no, wait, but that's not really
No,
recurring.
that's not the same.
Yeah, that's not really recurring. No, never mind, never mind.
Because you
Yeah,
have to have a 1 at some
yeah.
point,
As I
which
said, I was
then,
just thinking out loud. Just
yeah.
thinking out loud. Wasn't sure.
Yeah. This actually brings me to indeterminate forms. So an indeterminate form is when you have, like, let's say 1 to the infinity. Okay.
Mm-hmm.
So if you have 1 to the infinity, that's just equal to 1. But now let's say you have a function, um, like, uh, let's say 1 over x to the x, and you're trying to see what happens when the function goes to infinity. Well, the base goes to 0, but the exponent goes to infinity. So then you have this indeterminate form called 0 to the infinity. And then what you want to do, I'm not going to go into it like super rigorously, but you want to see which one approaches their goal faster. Because if, right, 0 to anything is just 0, right? So if the base reaches 0 faster than the exponent reaches infinity, then the answer will be 0. But if the exponent just reaches infinity way too quickly, then it will go to infinity,
Infinity.
or it'll have some weird behavior at infinity. And there are lots more indeterminate forms off the top of my head. Like uh, there's one to the infinity. There's infinity minus infinity.
There's infinity over. Isn't infinity over infinity indeterminate?
Yeah, it is. Yeah, it
Yeah,
is.
and then there's 0 over 0.
0 over 0, right?
There's 0 to the power of 0. Is that one? I don't know.
I don't think so.
I don't know. I
I
think that's
think,
just 0.
yeah, I think
Yeah,
that's
0 to
just
the power
0.
of 0 is just 0.
So yeah, an indeterminate form is just when you can't tell like off the bat what it's going to do. Like usually if you have x squared, it's just going to go to infinity. Or if you're
Yeah.
looking at the limit goes to 0, it's just going to be 0. But if you have a weird function where different parts are doing different things. Okay, so sorry, my computer fell asleep. But I was saying that if different parts have different behaviors, then you have to like something called L'Hopital's rule that you can apply, and you can see exactly what's going on. And L'Hopital's rule is if the limit exists of a certain function, and it's like you can decompose the function into a quotient of two functions, then if that limit exists, then the limit of the derivatives of the two functions, right, will exist and will also be the same
Yeah,
as the
but
original.
also a very important thing is that, so it's pretty much what he's trying to say. I can maybe put it into a mathematical sense where it's like the limit of f of x over g of x is the same as the limit of the derivative of f of x over the derivative of g of x.
Yeah, I was just trying to say it into words.
Yeah, I know, but and also this is only true if the limit of both f of x and g of x both exist. That's also important
Right.
because sometimes like they don't necessarily exist and you just differentiate them and you really get nowhere because that's not a right answer. Like they
Yeah.
both have to exist.
And that's a proof that we didn't do in class, because I went on YouTube and looked at a proof for L'Hopital's rule, and it's
Of
like 30
course you
minutes
did.
long.
Of course you did.
And it's not
No,
easy to
wait, we did a
understand.
L'Hopital proof in class.
No, we didn't.
I am 100% sure
I
we did a
swear
L'Hopital proof in class.
we absolutely did not. Like
Okay,
proving L'Hopital's rule, like proving that f of x over g of x, the limit is the same as f prime over g prime. We did not do that.
listen, I know I'm right and I'm going to find it, but not now because now we're going to talk about the podcast. But I will
Okay,
find it after for sure and I will show
please,
you
please.
because I am so. You know what? You know what? I might not be 100% certain, but I really think we did.
Okay, anyways, let's just move on.
You know what? Let's forget it. Let's forget it. Okay, so let's talk about other stuff. So, one thing I really wanted to talk about is so when we're talking about infinity and infinitesimal stuff, small things pretty much, one thing I really wanted to bring up is, especially going a little more into the physics tract, we can talk about something called Planck length, which is the smallest unit of length.
I
Now,
think
I
I
yeah,
think before we talk about Planck length, we should talk about infinitesimals and like what they are,
okay,
So
okay, sure,
yeah, so you have infinity, which is the largest number, quote unquote, and
yeah,
then you have an infinitesimal, which is denoted as dx, and it just represents like basically the opposite of infinity. Instead of it being like a really large number, think about the smallest number you can ever not even think of, right?
yeah, very very tiny number.
And it's really applicable in math, especially when you start doing like more advanced things.
Yeah, so in math, we can think of infinitesimals and really, really, really tiny numbers, but they're not really numbers. They're simply just notions. They're ideas, like dx, for example. But in real life, those things are not really true, right? And that's where Planck length comes in, which is the shortest possible unit of measure of distance. And it is the distance that light travels in 1 unit of Planck time. Now, Planck time and Planck length are pretty much all just versions of Max Planck's physics idea that everything is really, really tiny. And Planck's constant, the most like a very important constant in physics, is really where the entire idea of Planck stuff even came along. Because when you mess with numbers, you just, I'm not 100% sure of how to exactly get the Planck length, so I'm not going to lie to you and say something wrong on the podcast. But I'm sure Planck's constant has something to do with it. And pretty much what I'm trying to say is that Planck length being the shortest unit of measure is more of a physics idea than a math one. And the entire idea that we can apply infinitesimals and infinity to physics in the same way that we can do in math is also pretty interesting.
Yeah, in class, we didn't actually go into what Planck's constant is, right? I think he just like
We didn't really go into the, no.
uh, it came out when we were doing black body radiation, right? He's just like, don't think about the equation, just know that it has something to do with Boltzmann's constant and Planck's constant.
Classic physics professor move.
I'm sure we're gonna get into it. You
I
know,
mean, we are interviewing the physics professor soon.
that's true. That is something that
So
we should
we
ask
can
him.
actually ask him. Yeah, this is one of the questions. Okay, so spoiler alert. We are having another guest on the show, and it is going to be our physics professor from Physics 151 and 152 at the University of Toronto. And yeah, anyways, we're going to talk about that next time, but I kind of ruined the surprise. But I just wanted to make sure that we could actually ask that.
I don't think it's much of a surprise, but yeah,
I
because
mean,
we
it's a
had
surprise to like our 5 viewers, our 5 religious viewers. Very
yeah,
important.
because we had two professors. How it worked is that like the first half of the course was taught by one professor, and then the second half by another,
Mhm.
and then in the second semester it just went back to the first one, and then the second one again. We're going to interview both of them in separate episodes,
Oh,
and
wait, we got Professor Kushner as
yeah,
well?
yeah, I told you that.
Oh, that's awesome.
Yeah.
Okay,
So we got
okay.
a lot of they're both in different branches of physics, so we can, make our questions tailored for each of them.
Yeah,
That's going to
that's
be
actually going to be a
super,
lot of fun.
yeah, super fun.
Okay, you know what? Let's bring our focus more to this podcast instead of talking about the next one. We are very excited, extremely excited
Yeah.
for
So you were
soon.
talking about
Planck
Planck
length.
length.
Yeah. So also a really interesting thing. So if anyone watches Vsauce, I'm not going to take the credit for this because I did get it from there. But a really interesting thing is when we talk about the coldest temperature that is ever possible, we talk about absolute zero, right? Which is minus 273.15 degrees Celsius or something like that. But when we talk about the hottest temperature, no one really knows what the hottest temperature is. And once again, not by me, I'm not going to take the credit for this, but a really interesting concept of the hottest thing to ever exist. That will only happen when the wavelength of said material, of the radiation of said material, the wavelength is equal to Planck length. And when the wavelength equals
Oh,
Planck's length, that is the hottest temperature that anything can possibly be.
I never even thought of that.
Yeah. And that's really why I wanted to introduce Planck length, because I really thought that this concept of the hottest temperature in the world, or in the universe actually, is pretty cool, and it has something to do with Planck's length.
Is there like an estimation of what the temperature would be?
I don't really know. It's probably on, once again, the Vsauce video. I'm not 100% sure what it's called, but it probably has something to do with hottest temperature in the universe or something like that. Very interesting video, must watch. But I don't know if he really says the temperature. He probably does. I think it's something trillion Kelvin or something like that. I'm not 100% sure.
Hmm.
I'm not
Yeah,
100% sure.
I've seen like every single Vsauce video, but I don't remember like what he says because they're like 25 minutes long.
Oh, they're so
But
long, but they're so informative.
yeah, super super
Yeah.
informative. We were talking about infinitesimals,
Mm.
right? So one thing where those are super important is integration. So when you're trying
Oh.
to find the area under a curve, right, you can estimate the area by drawing like rectangles and be like, yeah, it's like kind of you can fit a few rectangles under the curve and be like, yeah, it's around this much. But if you actually want to find the actual area under a curve, you need to draw basically an infinite amount of rectangles that have height, whatever the function is at the point you're studying, and a width of dx, which I mentioned earlier was just a really really small number. And then what you do is you just add all those tiny rectangles with varying heights. You just do the sum from whatever point you're starting at to the point you're ending, and then you will, you know, get an answer. I mean, that seems really abstract
Hmm.
if you haven't done like the proofs and stuff like that. But like take my word for it. I guess it works.
Yeah, no, it's just a pretty interesting notion because it comes from Riemann sums and pretty much just adding infinite things together or taking something to infinity and then adding it together, because that's pretty much what we're doing. We're just taking the number of rectangles that there are, or we're taking the partition length to dx. That's pretty much what we're doing, right? And if the width of every partition, as you said, is dx, which is once again the smallest possible thing, we're pretty much taking infinite rectangles and adding them together, which comes from the Riemann sum. And understanding all of that kind of makes sense when we're talking about infinitesimals, because that has a direct application to, as Parker said, integrals, which are quite important in physics.
Yeah, I found it to be a really nice unit. We
Yeah.
started it as soon as we came back from the winter break, and before that, I've never like dealt with integrals. I think I've said that before. But yeah, we started like from the very basics, and then got to actually doing like integration methods and stuff like that.
Hmm.
And knowing like the foundation and then building off of that was just a really nice process, I think.
I think I told you this, but I actually originally learned integrals. Um, oh, this is a very embarrassing time in my life. In my grade 10 years, when I just came to Canada, I was really obsessed with Khan Academy, and I watched a lot of Khan Academy, and that's pretty much where I learned my integrals from. And I must say to anyone who hasn't watched Khan Academy, I 100% recommend it. I think Parker, you're watching it now too, right?
Yeah, I'm doing the cosmology and astronomy
It is
units.
so interesting, and he's like Sal Khan, like especially his videos are really good, and especially the math ones. The math he has like thousands of math videos. It's crazy.
He knows a lot of stuff. It's weird.
It's actually like it's I oh my gosh, I'm actually speechless. I don't have words for it. Literally, I can't think of words because it's so awesome that he has thousands of videos, especially with math and physics, because that's mainly how he where he started, and now he's branching out into other things. But especially with math and physics, he has so many videos that are just very, very, very well taught, I must say. And they just give kind of a person like me who wasn't really interested in math at all before that, which I think I have said before. A person like me actually got me interested in math, and that was
Yeah.
pretty much because of Khan Academy. And
So
I
if you
think
don't
that's really important.
if you don't really understand like what we're talking about right now, definitely recommended to go to
Hmm.
Khan Academy, because you don't have to, like, it's free, so you can just watch the videos, take a little bit of notes, and learn a lot about how interesting math can really be.
Yeah, there are a lot of really interesting theories and theorems, and we've actually discussed some of them in our previous video where we interviewed our math professor, and he was talking about some really interesting concepts that we, to be honest, weren't really understanding, but we tried to understand it. But it was really fun talking to him, and we really got to know, that even in math, Like there are some crazy theories that we couldn't even think about,
Yeah,
and
and there's
you know,
also a
kind
lot
of makes
of
sense.
branches that
Hmm.
you can go into. Like
Like
he was
C
talking
star
about like
algebra, what even is that?
yeah, I don't know. But
Like, yeah,
we're gonna become smarter over time, and we're gonna get to know. I mean, who knows? We might never even figure out what actually is C star algebras. We might
I
go
mean,
into
who
like a
knows
different branch
exactly?
because
Yeah,
it
but
seems
just
like
imagine that like 10, 15 years from now when we're like, more advanced in the field at least, maybe not still in the field, but definitely more advanced, more knowledgeable, and we
yeah,
come back on YouTube and watch these videos.
yeah.
It'll be a good memory.
I mean, the podcast is gonna evolve with our knowledge
Of
as
course,
well.
of course. But I'm just saying, watching like one of the first, like episode 5, episode 6, of this podcast,
Yeah.
it'll be a lot of fun.
Yeah, and especially when we start next year, we're gonna have a lot of topics to talk about, right? As soon as we
Oh,
learn something in class, we
true.
can just make a podcast, talk about it, and
Oh yeah, I don't even think about that. We're gonna have
like
so many ideas.
yeah, it's gonna be super cool. I know I
Yeah,
say
that's true.
super cool a lot, but it's true.
This is really gonna be super cool. I mean, super cool for the people who thoroughly enjoy math and physics.
Yeah.
I should say that. Not super cool for everyone.
Yeah, so we got kind of derailed on
Yeah,
our
we got
topics,
very much derailed in this
but
podcast, but I think we still enjoyed ourselves.
yeah, yeah, we are coming up on 30 minutes and something. So I guess we could just end it here. Um,
Yeah, this has been quite a lot of fun.
yeah,
Just got
we're
to
gonna
catch
be
up really with my buddy more than talk about the podcast.
we're gonna be recording, I think, another one like pretty soon, maybe like this week. It's Friday
Sure.
right now,
It's
so maybe
Friday right
like
now.
in a few days we'll record another one. We do have an interview on Tuesday that is gonna come out probably the week after that. Um,
We have a
depending on
lot of
how
time.
the schedule goes. Yeah, I hope you guys enjoyed this little discussion, and
Yeah.
yeah, we'll see you guys on the next episode.
I am Ray, and
I'm Parker.
we will see you soon.
Bye.